Okay, so let us work another problem together. Um, so we have a 660 kilogram race car. It's going to skid along the sidewalls of the racetrack for 3 seconds. Um, the force applied by the car is given. What is the change in velocity? So a few things I want to point out on this problem is I have a time. There's a force, which is time dependent. And that's what makes this problem interesting. So we turn our attention to the pink sheet. Is there a collision? Yeah, the car does hit the wall. Is there a rotation? In real life, probably, but in this problem, it wasn't discussed, so no. Do we have time? Yes, we have time. So we do the conservation of momentum, dp equals f dt, as our most likely starting point. So we parse the information that here's my wall. Initial. And this car is moving with some velocity. And then in the final state, 3 seconds later, horrible reproduction of that wall. The car, let's say it's up here someplace, and it's going to have a velocity as well. We should record that the mass of the car is 660 kilograms. Delta t was 3 seconds. And the force of friction, really in this case, is coming in as 390 t newtons per second. Okay, our question is, we want to find delta v, and we want to use dp is equal to f dt as our starting point. So our approach is dp f dt, and our system is going to be the car. So we do our representation, the final state of the car, and the initial state of the car. So we draw the bar charts we need. And what's nice here is I have just the car and just the car. Initially, the car is going to have some momentum. And finally, we expect that car to have less momentum. Looking strictly at the chart, what we should notice is that I haven't conserved anything. So we like to put impulse as the last part of this. And in order for final minus initial to work, I need to have a little bit of impulse that's positive, so that when I add this to this, I get this same basic height. So let's see if that holds water. So we start with dp f dot, f dot. No dot product there, just the force. Integrate both sides, and assuming that the car doesn't lose a lot of mass during the collision, I can take dp and just make it into the change in the car's momentum equals f. So I'm going to do this integral from 0 to 3 of our force, which was given up above as 390t, dt. We know our time, it slides through 3 seconds, so we have to do the integral first. So for the integration, we're going to get 390 divided by 2 t squared evaluated between 0 and 3. On the delta p side, what I want to do is I'm going to go mass v final minus mass v initial. Since what we're looking for is to find the change in the speed, I'm going to pull the mass out. So I have v final minus v initial. And we do. We have sufficiency. And we know everything else. So we'll just hold the 390 over 2, and we'll drop the 3 squared in place. Plus 0, which doesn't really impact us. So we're free to go to the next page, which just requires us to evaluate. So we write down what we had before. The evaluate is delta V is equal to 390 over 2 times the mass and the 3 seconds squared. So fortunately for us, this is all calculator math, because we know the mass from the first page was 660 kilograms. So up here I can say delta V is equal to 390 divided by 2 times 660, and then I'm going to multiply it by 3 squared. And we just plug and chug into our calculator for this. So 390 divided by 2 divided by 660 gives me a number, and that's going to be multiplied by 9. And my change in my velocity given these numbers is 2.65. Let's check the units. Well, one thing we have to be clear on is we're losing speed here. So that would imply that the force probably had to be negative. But we were just asked for the change in speed, somehow the wall is helping the car push along. So let's figure out the units. So the 390, which came from the force, carried with it newtons per second. And I have them over here, a second squared. And I'm dividing it by the 2 has no units. The mass is kilograms. And this is not the unit for speed, but it can be if we unpacked the Newton. The Newton is a kilogram meter over second squared. That's the Newton part. I'm still divided by seconds. I'm still divided by kilograms. And then I have seconds squared over here. So the second squareds are going to cancel. The kilograms are going to cancel. And right there in the middle, we get meters per second. Is the answer reasonable? To me, it seems low. It frankly ought to be negative, because we would expect the final velocity to be lower than the initial velocity.